So what are the implications of power factor and reactive power compensation on our grid? Here we've got a little mock-up of a grid with an industrial load shown on the left and a little wind farm shown on the right with a transmission line between them. The load in our industrial factory might look a little bit like this. Here we've got some resistance and some inductance. And that inductance might represent, for example, induction machines or HVAC or IT equipment, and the resistance represents the proportion of the load that is real, the part that the consumer pays for. This means because we have a reactive component to our load on our industrial side, we have reactive power flowing between our generator on the right and our consumer on the left. That reactive power doesn't do work, but it still needs to flow in the transmission network. And if we take a closer look at that transmission network, we'll see that all of our wires that join our generator to our load have a little bit of resistance. And so that current that's flowing due to reactive power has to pass back and forth across that resistance with time. And as it does so, it dissipates real power. That's real power that the consumer isn't paying for, but is still being used. That real power leads to heating of the lines. It also means that those lines need to be rated to withstand that additional real power. This creates a problem for managing reactive power in our grids. So how do we solve this? Well, for large industrial loads, we might require that they have something like a capacitor bank. In this case, a capacitor bank can compensate for that reactive power that's due to the inductance in the load. If you cast your mind back a few slides, we'll remember that the reactive power due to a capacitor is 180 degrees out of phase with respect to the reactive power through an inductor. So if we place enough capacitance in parallel with our load, we can compensate for the inductive reactive power. Now the reactive power flow is simply just between the capacitor bank and the factory rather than through our transmission line. Let's take a look at another example. In this case, we've got a domestic load. Like before, we have a mock-up of a grid. We have a wind farm, for example, on the right-hand side going through a transformer into a high-voltage transmission network, and then another transformer that converts us down to the street-level power we all see at our wall sockets. In this case, it's infeasible for us to ask the consumer to have capacitor banks in their home. And so that reactive power flow is forced to flow through that low voltage transmission network, but we can prevent it from traveling through the much larger and longer range high voltage transmission network by placing reactive power compensation at the low voltage transformer. And so our reactive power flow is now confined between the domestic load and your local substation.